Let's take a look at the behavior of gases from a molecular perspective. So, when we looked at the gas laws before, I mentioned that the gas laws were observed by scientists hundreds of years ago, but they weren't really explained. They didn't have a reason for why these gas laws were true. But it turns out that if we consider a gas as being made up of many molecules, and then we make some assumptions about the behavior of those molecules, then we can explain the gas laws. So the assumptions that we will make are as follows. Number one, a gas is made up of identical particles. All right. Number two, the particles in the gas are in constant random motion. We call this Brownian motion. Number three, the particles have negligible size compared to the container that they're within and compared to the distance between the molecules. Number four, all of the collisions between the molecules are elastic, so no energy is lost in those collisions. Number five, there are no intermolecular forces except during the collisions. Number six, the collisions are instantaneous. And number seven, the external forces on the molecules in the gas, like gravity, for example, are negligible. If we make those assumptions, then we can do something really impressive and really important. We can relate the behavior of individual molecules to the large-scale properties of the gas. We can relate the microscopic behavior to the macroscopic, the large-scale behavior of the gas. And as an example, let's consider Boyle's law. Now, Boyle's law says that the pressure is inversely proportional to the volume if the mass of the gas is fixed and the temperature it stays the same. So let's think about this in terms of the molecules. So let's say we have these molecules and they're trapped in a box and they're moving all around like that. If the volume decreases, then we would expect that there would be more collisions per second. And if there's more collisions with the sides per second, then the pressure should increase, right? There's more of these collisions, which means they're applying more force per second, and so the pressure goes up. Likewise, if we were to increase the volume, then there are fewer collisions with the sides per second, which means there's less force that's being applied per area per second, and so the pressure is going to go down. And you can follow similar arguments for the other gas laws, but I'll leave that to you. Instead, let's switch gears to something a little more mathematical. What I want to do is I want to try to find a relationship between the pressure of the gas and the speed of the individual molecules within the gas. And to do this, let's imagine we have a volume, cubic volume. Each side has a length L. So then the volume that we're talking about is L cubed. So here's our little box. If we have a collision with the side, one molecule collides with the side of the box, and we're going to have the molecule going straight on towards one side of the box. It impacts straight on with a speed v and bounces back with a speed v. So therefore, the change in the momentum of this molecule is, let's see, well, mv minus negative mv, because the final momentum is m times v and the initial momentum is negative mv. So the change in the momentum of this molecule is 2mv. Okay, now speed is just distance divided by time. And the time between the collisions with one wall is equal to, well, let's see, if we're talking about the same wall, v is equal to 2L, because if it's going to hit the same wall, then the distance that it travels is 2L. So the speed then is 2L over t. So the time between collisions with the same wall is 2L over v. So let's see. The average force that's applied on this wall is equal to the change in the momentum over the time that it takes to change the momentum. So let's see, the change in the momentum is 2mv, and the time that it takes on average for it to hit the wall is 2L over v. So then we get that the force that's applied by one molecule on one wall is mv squared over L. All right. Now, the pressure that is applied is equal to the force per area. So let's see, the force expression that we have is mv squared over L, and then we have area in the denominator, but the area is L squared. Okay, so now we have mv squared over L times L squared, or mv squared over L cubed. So that's the same as mv squared over the volume. Now, here's where it gets a little fuzzy. In reality, the molecules are not moving in one dimension. The way that I've explained this and argued everything, it's been moving along a single line. But in reality, they're moving in 3D. So without explanation, I'm going to include a factor of 1/3 to account for that. And we come up with this expression. The pressure that's applied is equal to 1/3 times mv squared over the volume. And m over v, if we're considering all of the molecules here, then that is equal to the density of the gas. So we end up with this expression. The pressure is equal to 1/3 times the density of the gas times v squared. Now I want to point out that v squared right there, that is an average. And specifically, it's the average of v squared, which is different than the square of the average of v. And that's kind of a weird little detail, but I just want to make sure that I mention that. Um, but the power of this expression is that it relates the behavior of individual molecules. In other words, that v, that speed of the individual molecules, it relates that to a property of the gas pressure. It's relating the microscopic behavior of the molecules to the macroscopic behavior of the gas. Now, let's shift gears again to an energy perspective. So before we saw that an ideal gas has no potential energy. It only has kinetic energy. It has no potential energy because there's no intermolecular forces. So what we can say is that the internal energy, U, is equal to the kinetic energy of the gas, 1/2 mv squared, times the number of molecules in the gas, N. Now, if we're talking about an ideal gas, we also have the ideal gas equation, PV equals nRT. But now we have this expression for the pressure. So let's use that. Pressure is equal to 1/3 times the density times V squared. Okay, we put that in there. Um, and now I'm going to say that the density is equal to the number of molecules times the mass of each individual molecule divided by the volume, which means it simplifies to 1/3 times the number of molecules times the mass per molecule times V squared, and that's equal to nRT. Okay, here's where it gets a little interesting. So the internal energy of the gas is 1/2 mv squared times N. So that means that 2/3 of the internal energy of the gas is equal to 2/3 times 1/2 mv squared times N. So 2/3 of the internal energy of the gas is equal to 1/3 of mv squared times N. Well, wait a minute. 1/3 times mv squared times N. Hey, that looks just like that expression we had up there, which was equal to N times R times T. So 2/3 of the internal energy of the gas is equal to nRT, which means that the internal energy of the gas is equal to 3/2 nRT. Or, going even further, we can use the fact that the Boltzmann's constant is equal to the ideal gas constant over Avogadro's number. So the internal energy of the gas is equal to 3/2 times N times Boltzmann's constant times the temperature. Now compare this to the average kinetic energy per molecule expression that we had before. Before we said that the average kinetic energy per molecule is equal to 3/2 K times T. Well, hey, if we take the average kinetic energy per molecule and multiply it by the number of molecules, we should get the internal energy of the gas. And we do. All right. Now, I also want to focus in on the differences between real gases and ideal gases, because we've been talking about ideal gases, but remember, they're an approximation. I can't go down to the store and buy an ideal gas. I can only buy real gases. Now, real gases behave a lot like ideal gases when the intermolecular forces are negligible, right? That's the big assumption of an ideal gas. This is not true, however. This assumption does not hold when the density is very high. And the reason for that is because if the density is very high, then the molecules must be very, very close together. And then those intermolecular forces that are there become important and have a big effect. And so it no longer behaves like an ideal gas. It also doesn't work if we have high pressure. If there's a high pressure, then that means that there's going to be many, many collisions. That means that there's many, many opportunities for these molecules to be close together. And if they're close together, then those intermolecular forces will become important and have a big effect on their behavior. Also, real gases don't behave like ideal gases at very low temperatures. And that's because, in that case, the molecules tend to be moving very slowly, which means that the molecules kind of loiter near each other when they come close together. They spend a lot of time near each other when they kind of pass by, and they have a lot of opportunities for the intermolecular forces to be important. And so, in those cases, the real gases do not behave like ideal gases.